Hello guys, welcome back. This is Rosario Borgesi and today we will discuss a great topic of Solidity, which is the contract. So we will see what are the building blocks of a smart contract, like variables, functions, events, custom errors and so on. So we will move from these basic topics to much more difficult topic like abstraction and polymorphism. So this will be a great video with a lot to cover, and let's get started. I created this medium story that will guide us throughout the whole video, and we can start by from the basics of a smart contract, a Solidity smart contract. A Solidity smart contract can be compared to a class of a programming language like Java. And as you can see here, the structure is very similar to a Java class. The main difference would be that at the start of a smart contract, we have to specify which is the compiler version. So as you see here, Pragma Solidity 0.8.25, which is this is the version, the Solidity version of the compiler. Then we define the contract similar to a class. We have the state variables here. Then you have a function which is defined with the function keyword. This is an event that it is a component of the Solidity language that allow us to log some data on the blockchain. Here, for example, we are storing this number just for the sake of the presentation. So it is used basically to store some data on the to log some data on the blockchain. And then here we have another example of a simple function. Let's see now how we can create a contract. So contracts can be created externally via Ethereum transaction or from within the contract, the Solidity contract itself by means of the new keyword. Much like you would create a new object in Java, for example. Then there is an IDE which is Remix, which is it is very used to create to develop some smart contracts and to test them, which is here, and we will use it throughout the video. And of course, it is also possible to create to create contracts to deploy them by means of the JavaScript libraries that allow us to interact with the smart contracts, which are web3.js and ethers.js. An example of this on how to interact with the smart contract with ether.js you can find in my other video developing a smart contract with RDAT, because RDAT is a framework that makes use of ethers.js in order to deploy smart contract and also to interact with them. So basically, like in Java, there is to create a new contract, there is a special function which is the constructor, and it is denoted with the constructor keyword. It is important to understand that once the constructor has completed its execution, the code of the contract, the final code, it is deployed on the blockchain, but the functions that are deployed do not include the constructor itself and um, the internal function that are called inside the constructor. For example, we can make a test with this contract here on Remix. We copy it, and so we go on a test. We create a test contract here. As you can see, this contract has an address variable which is owner, which is public, and this means that Solidity, as we will see later on, will also create a getter for this variable. Then there is the constructor, which is basically setting this variable to message dot sender, which is the address that is deploying the contract, which is my address in this case. Then this contract define this function division here that takes two argument uint. If you don't know the types, these are the types of the parameter here. Of type uint, which means integer. And this function makes use of the only owner modifier. The modifier is this one. We will also talk about it in the next session, which basically performs some validation. Here we are making sure that the contract that is calling this function here, division, it is the owner of the contract itself. So another address cannot call the division function. Then here we perform some basic validation inside the division function. We require that the denominator must be greater than 0. Otherwise, the division is not um, it is not possible to perform the division. And so we can deploy this contract. We just need a MetaMask account. For example, I already have a MetaMask account here. It is very easy to create a MetaMask account. You can find all an article that describes it in the description. So I log in into my account. As you can see here, I have some Sepolia ethers, test ethers, because this is a test network here, Sepolia. So because we do not test the contract in the main net, because we would pay real ethers, but we test the contract in the test network, so we can make use of the test ethers and we don't pay real money. The ethers can be acquired here in Sepolia by means of a faucet. You can find the two link in the description. For example, I use the alchemy faucet, which gives you 0.5 ethers each day. So now the contract has been deployed because here you have the compiler. The contract is auto-compiled, so at the version 0.8.25. Then here in this section we can deploy the contract. We can deploy it either in the this is a local test network that is created by Remix in the browser, but as you can see, it is not working because I have 0 ether. And I can also deploy it into Sepolia. I need to select here injected provider MetaMask. So I select this. As you can see, this is the account that we have here. it is the same. So I press here deploy. It starts the transaction deployment. I confirm. Here it is logging. Okay, the contract has been deployed. I can see an instance of the contract here. And as you can see here, you have two functions. The owner, which is the getter I was talking about before, that gets auto created because this variable is public, which is exactly the same of my account, which ends with FE28. So here this contract, this account ends with FE28. Okay, then the division I put here, I want to divide 10, I want to perform this operation 10 divided by 2. So this divisions gives us, this operation gives us 5. But if I try to call this function with another account, my second account, and I want to call this function again, as you can see here, the execution has been reverted because this function can only called by the owner of the contract. So um, this is what this line of code here it is doing. As we said earlier, it will prevent that an account different from the owner, as you can see here, can call this function. But of course, there is another validation that we are making here. We are requiring that the denominator, the y must be greater than 0. So if here I put 0 as second argument, this is the first and this is the second argument, and I call this function, of course, here the execution is reverted. This function can only be called, but sorry. Okay. I forgot to switch the account. Now I can call it again. Okay. Execution reverted. The number must be greater than 0. So it is calling this require here. So this is a basic example of contract. Okay. Now let's discuss variables. What are variables? In a programming language, a variable is simply memory location with this which has a name, and so you can basically store data type and information and data in the memory. But of course there are different types of information that you can save in a variable. For example, you can save boolean, string, an integer, and so on. So there are different type for each type of information that you want to store, and for this, if you want to deep dive into this into the data types and know more about it, I suggest you um, to check out the video that you will find above that is dedicated to Solidity data types. However, to define a variable, we need to specify the type, the data location, but only for the reference types, which are mappings, arrays, and structs. The visibility is not, it is optional, and the name of the variable. As you can see here, the data type of the variable can be, for example, uint, int, address, bool, and so on. The data location can be memory, storage, or call data for complex types. The visibility can be public, private, internal, or external. This we'll discuss later on. And of course, at last you have the name of the variable. Um, of course, the type not only indicates the kind of information that we want to store, if it is an integer, a boolean, string, whatever, but it also determines the size, the amount of memory that you are going to occupy with this type of variable, because of course, for example, for integers, there are integer with 8 bytes and integer up to 225 bytes. So we should choose carefully the type according to our needs. As we said earlier, the no, sorry, there are two types of variables: state variables and local variables. State variables, it is are this variable here defined outside the function, while local variables are defined inside the functions. So, in fact, the state variables have a contract-wide scope, so you can reach them from any function in the contract. The storage are permanently stored in the contract, so they have um, their location is of type storage, and they live as long as the contract lives. So here, as I was saying, there are various data location that you will find more in the video about the types. Memory means that it is the variable is stored in memory. Storage means that it is stored in the blockchain. Cold data, it is a read-only um, um, a read-only location that it used mainly for arguments. And of course, you have local variables, which are scoped to the function in which they are declared. They are stored in memory, and their lifetime is limited to the lifetime of the function where they are defined. So here you can find an example. This is a state variable. So um, it is similar to a Java instance variable, and very similar to Java also. You have a local variable which is defined inside a function. Then we have the state visibility of the function, which we anticipated before. So when we declare a variable as internal, it can be accessed only from the contract in which they are declared and from the contracts that inherit from this base contract. And this is the default visibility level, while there are also public state variables that are with respect to they are similar to internal variables, but they add, as we said earlier, a getter function which allow them to be, which can be called externally from the contract. And so it is not possible, even though there is this, even though they are this variable are declared as public, they cannot be modified externally from the contract. So uh, here you can grasp a little bit of the encapsulation principle of the object oriented programming. Then you have the private variable. Private state variable are like the internal, but they are not visible in the derived contract. So they are only visible in the um, in the um, in the contract itself. Then you have, as we said earlier, the getters. So for all For all public state variables, the compiler automatically will create a getter. There is a difference, however, between value types and reference types, because, for example, for a value type like could be uint or address that we have seen before, the here the getter returns the value of this variable. For example, here if we call int var this getter, it will return 1, while if we call the getter of this variable, it will return a getter that in which we must specify what index we want to retrieve, because it for gas to avoid excessive gas cost, it will not return the whole array. But if we want to to retrieve the whole array, we just need to write our own function like this here. So if we call this function here get all array, the whole array will be returned. So we could also, for example, give it a try here. So we delete the previous contract, we deploy this one. Okay, we get the instance of our contract, for example. The variable int var, the first one, here returns 1. Okay. If we call array var here, we have to specify the index. For example, we say 2, and we expect to get 3. Okay. If we put 3, for example, we should get. Okay, the transaction is being reverted, of course, because it has just 3 elements, 0, 1, and 2. Of course, if we call here get all array, it will return the whole array. Let's talk about constant and immutable state variables. So, state variables may be designated as either constant or immutable, and in both scenarios, these variables are unchangeable post-contract creation, but while constant variables require their values to be set during the compilation process, immutable values permit value assignment at the time of contract construction. So, of course, it is not worthy that constant and immutable values compared to standard state variables incur in lower gas costs. And however, it is important to recall that not all the types are currently supported for constants and immutables. At this moment, only strings and value types. So this is an example that makes use of immutable variables and constant variables. We can try it on Remix. So these immutable variables may be modified during the constructor. So here we are setting it at 18. Then when we call the constructor, this value is replaced with the argument of this constructor here, while the constant variables cannot be modified. So, for example, if we deploy this contract, here we put, for example, we want to put 25 decimals, that we should find after we deploy the contract that this variable, the getter of this variable, should return 25. So we deploy it. Okay, we confirm the transaction. Okay. Here we find that decimals is 25 as expected, so its value has been replaced with the one that we have provided in the constructor, and of course my hash will be this algorithm here applied to this string. Okay, the owner will be always my address, and text variable, which is a constant, we will be unchanged, and it will be ABC. Here there is a simple modifier where we are requiring that this number here that we are providing in the constructor, this argument should be greater than 0. So if we provide a value equal to 0, it should the transaction should revert. So let's talk about now functions. So functions are present in every programming language, and it is basically a function. It is a block of code that executes some tasks. So it comprises a set of instruction that are executed when the function it is invoked. So here are the keywords that we will need to declare a function. So we have the function keyword, then we add the function name, the parameters of the function, the visibility, mutability, parameters of mutability, keywords of mutability, modifiers, and the return types. So the function names, the name of the function, there are parameters that the function accepts. Then we have the visibility that can be one between public, private, internal, or external. We will discuss this later on. Also, the mutability can be pure, view, or payable, or blank, which implies non-payable. Also, this will be discussed later on. And also, we have the modifiers, as we have seen earlier for here. For example, is greater than 0 that can be used to perform some validation or to change the behavior of the function, and there are return types, which means what type the function will return. So this is an example, as you can see here, of a simple function which you have declared, which we have called the square, that takes an argument as input and calculates the square and returns the square of the input. So the function it is public. Pure it is the, as we said, the mutability parameter, and then we have here returns the type that the function will return. So in this case, we return a uint. So keep in mind that here it is returns, while here inside the function it is called the return. And of course, function can be defined either inside a contract but also outside a contract. And then we have also, if you like, we can also test this function out. Here we, for example, we deploy this function, confirm. Okay. Here, for example, we pass 3, so we expect that square returns 9. Okay, it is working. So function parameters are declared as the same way as the variables, and they are the input of the function. For example, here we have the two parameters, which are strings. Here we need to add the memory because this this for the strings we have to specify the location, so it would be memory in this case, while and this function concatenate returns the string concatenation of the two input string, while here we have a function that calculates this returns the sum of these two inputs here. So also this function could be tested on Remix. So we deploy this function. In the case of string, also in the returns, we have to provide the memory, the location. So in this case, it is memory, but could also have been, for example, called data. So here concatenate, we pass, for example, hello, and then as a second argument, world, we put a space here. We call this function. Okay, it is it has returned the whole string, has removed the space. So let's try if I put a space here, for example. No, it is the same result. Okay. Then here we have some. For example, we put here 10 and 5, and it returns 15. Okay. Um, So, okay, the input parameters could be of any type supported by Solidity, including booleans, arrays, structs, mappings, so on and so forth. Okay, then there is the return variables that are declared after return scale word, as we have said earlier. And the curious part here is that in Solidity a function can return also multiple outputs, like for example with the tuples in Scala, for example. But there are some language that don't allow this. Like for example, Java does not allow natively to return multiple outputs. Here, for example, we could try this code. So we deploy this contract. Okay. Here we pass 10 and 5, for example, we call operation. Okay. So the sum would be 15 and the product would be 50. So you can have also you can return two values in Solidity. In this case, in the second example here, the difference is with respect to the previous one is that here we are providing the return statement while here not, but they work the same. So we cannot return a specific set of types from non-internal function. This includes mappings, internal function types, reference type with location set to storage, multi-dimensional arrays, and structs. Now let's talk about function visibility. As we said earlier, here in the function we can express the visibility of the function, which could be external, which means that the function can be called from the outside of the contract, but not from the within the contract itself. Can be public. The function can be called both from within the contract and from outside of it, and could be internal. The function can only be called from within the contract or contracts inheriting from the contract. in which is the function, and private where the function is visible only from within the contract but not from contracts inheriting from it. And here there are some example. So you change here um, the function visibility. So here you have a private function, external function, public function, and another internal function. Also this, for example, we can say that what we have said it's true. So we paste this code here, we deploy this. I can remove this. Okay, we are deploying. Confirm. It is a little. Okay, here it has deployed the contract. Okay, as you can see, the only variable that I can see from the outside are set data and get data. Set data is external, get data is public. I cannot see F because it is private, neither I can see compute because it is internal. So if I put here set data, for example, 10, okay, I confirm the transaction. Here also it has not created the getter for this variable because this variable is private. If I go get data, I get 10. So perfect. Then we can talk about the state mutability. There are various types of state we can set various different types of state mutability, which are view, pure, um, and also view pure basically. So we have what is a view? What are view function? Are function declared as view do not modify the state. Do not modify the state means that they do not do these things listed here. They do not write to state variables, emit events, create other contract, send ethers via call, use self-destruct, call any function not marked as view or pure, use low-level calls, and use inline assembly that contains a certain type of optocodes. This is an example of a view function. So for example, here what we are doing, we are reading the variable here of R1, but we are not modifying it. So this function can be marked as view. And also the getter methods are also automatically marked as view. Then there are pure functions. Function declared as pure do not read neither modified state. Here we are reading the state, so we cannot read the state to have a pure function. And so, in addition to the condition that we have explained before, there are also these conditions that must be satisfied in order for a function um, to be considered as pure. They do not have to read from state variables, access the balance with address this dot balance, access any of the members of this special variable block, ticks, and MSG. Cannot call any function that it is not marked as pure, and cannot use inline assembly with the determined opcodes. As you can see here, this var1 is not used, so this function can be marked as pure because here we are not using it. Perfect. So then we can talk about some special function. There are functions that, for example, function um, to receive either function. What is a receive either function? A receive function is a special function that allows a contract to receive ether, which means, and by the way, it is permitted for a contract to have only one receive function, and it is defined, as you can see here, receive external payable. Okay, and we can omit the function keyword. This function cannot accept any arguments, it is not allowed to return values, and it must be designated as external and payable. It can be additional, it has the flexibility to be virtual, to override other functions, and to incorporate modifiers, okay? So the receive function is automatically invoked when the contract received a call with no data attached, commonly known as empty data, and this typically occurs during straightforward Ether transactions such as those made using .send or .transfer. This means that, as we will see in this example, we get the address of the contract and we call this is a member of the address type. It is explained in the video of the data types that I have suggested before. The address type has two members, .send and .transfer. So let's try this code to demonstrate this. So this code has two contracts, a receiver contract, which has the receive function that it is designed to receive the, the ether, and as a function get balance to check the balance of this contract, okay, that we will use for testing purposes. Then we have also here there is a getter auto created, of course, because this function is this variable is public. Then we have another contract called sender that also has this variable here that can be used to check the address of the sender method, sender contract, sorry. Then there is a constructor which is payable, and so it means that during deployment we can provide some ether. So we transfer some ether from our account to this contract, and here this require is used to make sure that the ether that this contract is receiving, message dot value means the ether that have been sent during the deployment, are greater or equal than 0.001 ether. Otherwise, the transaction will revert. So we are making sure that this contract has at least this amount of ether on deployment. Then here it is being defined the send ether function that receives as argument an address which is the receiver and the amount of ether that we want to send. We of course require that this contract, okay, the sender contract has a balance, of course, that must be greater than the amount of money that we want to send, of course, otherwise it is not possible to execute this transaction. Then then we call on this address payable that we are receiving here as argument the transfer function. So it means that we are transferring this amount of ether that we receive on input to this address function from the sender contract, and then we emit an event just to log this this operation on the blockchain to make a log. And here also we have a get balance method that returns the balance of the sender contract. So we should first deploy the sender method. To deploy the sender method, we should pass at least this amount of ether that we must convert into way, because here we have to express the value in way. We cannot express ether in with the decimal part, only integer numbers. So here we use this simple converter to we put the amount of ether and it converts it for us in ways. We copy this value away, we put this value here, and so we deploy the sender. Okay, we confirm. Perfect. The sender contract it has been deployed. You can see the balance. It should be equal to the one that we have pasted here before. And the sender address is this one. Then we can also deploy the um, the receiver method, the receiver contract, sorry, which has to receive the ether. We deploy this contract. Perfect. The receiver has been deployed. So we now take this. Of course, the balance is here is zero because we have not provided any ether, and the receiver address is this one. Now we want to send some ether from this account, from this contract to this one. To do that, we copy this address here, which is the address of this receiver, and we call send ether. We pass here the address and the amount with zero. We should put the amount in way. So we take the decimal part that we have deployed. Here we put this amount here and we transact. Okay, maybe let me try. I have not expressed it. It has warned me that the transaction was likely to fail, but I didn't listen. Maybe I expressed not. Okay, I should have put maybe this the quotes. I should have quoted it. No, this transaction is likely to fail. Ah, maybe I'm spending too much because here the total of the transaction will be 0.009. So we are sending this as, of course, um, this has of course 0.001 ether, so it is possible. Okay, now I understand why. Let's reject this transaction. Okay. As you can see here, if I call get the balance, the value is not changed because the transaction has been reverted. So if we paste this here, it's still 0.001 ether. So let's Let's put zero more. Maybe I did the reverse. That was my mistake. Okay, I believe I will copy. I don't remember if I copied. Okay, so now we should place this here. Okay, let's transact. Okay, now there is no problem. Okay, because I put the wrong value. Perfect. Okay, the transaction is okay. So always um, check the warnings of MetaMask when something when it warns you. Okay, now the receiver we see the balance that we have sent. Okay, if I go get balance, I will see the same value here. Perfect. So it works. Now, of course, here you have um, the balance of this the sender has been reduced by the amount that we have sent to the receiver contract. So it worked perfectly. So this is an important another important example. Then here in this article I reported the concept of a fallback function, which is a function that allows you to receive either if there is no receive function, but the documentation suggests to make use of the receive function. So this fallback function basically has use case, as I have understood, it is mainly used when in the delegate proxy pattern, and uh, which is used in the upgradable smart contract pattern, where that also for this I have created a video, and you will find it in the link up above in the video. So let's now talk about the function overloading. Overloading means that you can call essentially, as in other languages, like for example Java, you can create two functions with the same name but with a different signature, and so it is possible to define this in also to do this also in Solidity. Then we have the concept of function modifier that we have seen a little bit earlier. So a function modifier is used to perform a validation, for example, on the input of a function. For example, we need to verify a condition before executing a particular function. If the condition is not satisfied, then the function will not be executed. With each modifier, we need to express this underscore with this semicolon. This means that where we put the modifier, for example, here in this function, here Solidity will replace the body of this function. So if we apply this modifier to the division function, here it goes return x divided by y. Okay, and so this is an example that we've seen earlier. So here we are making sure that the y is greater than 0, otherwise it is not possible to make the division. It is the same that we have seen earlier. So we can also give a try to this one. Okay, I delete. Okay, I'm deploying this contract again. Okay. Here, for example, I go 10 divided by 2. Okay, and it works 5. If I put here 0, okay, the transaction is reverted, the number must be greater than 0. Okay, perfect. So then we have the event that we have anticipated before. Events in Solidity create a permanent record on the blockchain, ensuring that all activities are transparently logged. This is useful, for example, for an audit or the validation of the integrity of a transaction, and also to check the validation of interaction with a smart contract. And we have seen an example earlier, but we can also use this code to see it another time. So we have an event division, okay, that gets called here when we call the division function. So it is the same code that we had before. Here we are triggering the event. So if we deploy this contract, here I call 10 divided by 5. Okay. Okay. Here you can here you can see in the logs part of the transaction receipt, you can see event division args. First argument is the address, because here we have message.sender, so it is who is calling this function. First argument you have 10, second argument you have 5, and so this is basically it for event. Well, for some reason, when we called the division operation, it did not display the return value of the division. So I added a test function to make sure that it returns the correct value. So we can deploy this contract. Maybe it is just a front-end problem. I want to make sure that it is working. So here we have the function. If we call division as earlier 10 and 5, it calls the division, the function, but as you can see here, it does not return the value. So here, okay, it gives us it emits the event, but does not return the value. So I wrote this function here to make sure that it does return the correct value here. So we run this function test. Perfect, it is working. So okay, it is maybe just a front-end problem or remix. Okay, this is that should be it for events. Then we can talk about custom errors. So in Solidity, we can define our errors that enable us to assign to these errors some descriptive names to understand why a function um, has failed. And these errors can be used with two statements, which are the revert statement and the require statement. Here there is an example. Now the problem is that to use with the require function uh, the error here, we need Solidity version 0.8.26, but it is not available right now. So even though in the documentation of the 0.8.26 it is possible to make this declaration, it is still not working because the maximum value of the compiler, Solidity compiler, it is 0.8.25, so we cannot test it right now. However, here we define our error, which is number not valid. So we define two function. One division with error, which if the y is 0, reverts with the error number not valid 0. Here we are using the version with not the custom error, but with the string, because this is an overload um, of the require declaration. And also here return the x divided by y, waiting for the solidity 0.8.26, where we can use this the error inside the require function. So also these can be tested. For example, if we put 10 and 5, it works. Also here, perfect. If here we put 0, reverse. Okay, number not valid. Here also if we put 0, this is division with the revert error. So this is this one, as you can see. Error provided by the contract, number not valid, parameter y, y value 0. So here it should return something like this when the compiler it will be available. So this is a very common pattern to use the custom errors to explain to the user why your function has reverted. Okay, here we are explaining the same things that we said earlier. Okay, here we are saying that errors are not subject to overloading or override, but they can be inherited. Okay, here the same story that we have said earlier. Error instance can only be generated using a revert statement or as second parameter in require function. Okay, then we can talk about inheritance. Um, Inheritance means that a contract can access all non-private components of another contract. Because as we said earlier, the private visibility does not allow to See, for example, a variable in a derived contract, including state variables and internal functions. So a contract can access all non-private components of another contract, including state variables and internal function. The contract that inherits from other contract is referred to as derived contract, while the contracts from which it inherits um, are known as base contract. To make a contract extend another contract or inherit from another contract, we use the is keyword. This is pretty much the same as the extend keyword in Java. Solidity supports multiple inheritance, including polymorphism. Polymorphism means that a function call, internal and external, always executes the function of the same name and the parameter types in the most derived contract in the inheritance hierarchy. Um, of course, this has to be enabled, enabled by using the keywords virtual and override. Of course, polymorphism, as you know from object-oriented, it is a core principle of the object-oriented programming, and maybe in the future I should also create a video about object-oriented programming in Solidity. But for now, let's say that it is possible to invoke function that higher up in the inheritance in this way: contract dot function name, using um, this expression here, or using this super like in Java dot function name. Okay, a contract can also inherit from multiple contracts, and okay, a state variable x can only be declared in a derived contract if there isn't any visible state variable with the same name present in any of the base contracts. So here there is an example, because the theory is fine, but without practical example, we do not understand what we are talking about. So we have defined an owned contract here, which is using the same pattern that we have seen at the beginning of the video. So we have the owner. In the constructor, we set the owner as message.sender, and we define the modifier only owner, which perform this validation that the sender is the same address, which calling this function is the function is the same address of the owner. Then we define some contract which are inheriting from owned, so they inherit this modifier here, and so we can use the only owner modifier in the function, for example, sum here, or subtraction, the same story. Here we are inheriting the only owner um, modifier, and we are defining the subtraction. Here we are defining the sum. Multiplication, we define the multiplication operation. Here we define also the divide operation. Then we create a final contract, arithmetic operation, that will inherit from all these four contracts. So it will have all these functions: sum, subtract, supply, and divide. We can test this contract by deploying the last contract, the final contract, which is at arithmetic operation. We deploy it. Okay, it takes a while. Okay, the contract has been deployed. Okay, as you can see, we see all the function of this contract. So this is the base contract, this is the derived contract of this contract, and all of these are the base contract of this derived contract. So the owner is always my address. Then we call divide, for example, 10 divided by 2, we expect 5. Okay, multiply 2 times 3, which gives 6, subtract 10 to don't know, 9, which gives us 1, and sum 6 plus 8 gives us returns 14. Perfect. So this is the inheritance in action. Perfect. So okay. Now here we are demonstrating the super keyword. So we are calling from this derived contract the function f of the base contract, exactly as you would do in Java. So you copy this contract here, okay, and we deploy the derived contract. So we expect when we call the g function to see the contract should print out. We see both the function, of course, because the derived contract inherits from the base contract, so inherits all the state variables of the base contract plus the function, and also it has its own function. Okay, so this function f returns this is the base contract function. Here instead it should return derived contract function plus this string here, because here we're calling this function with super.f. So if we call g, okay, it returns derived contract function. This is the base contract function, so it is working. Perfect. Then you can also override a function, and this also has to do with polymorphism. To override a function, we need to mark the base function as virtual, and the function in the derived contract that overrides the base function with the override keyword. Here there are some configuration. Okay, if the visibility of the function being overridden can only be altered from external to public by the overriding function, and the mutability can be adjusted to a stricter form. For example, non-payable can be overridden by view and pure, and view can be overridden by pure. However, payable is an exception, and its mutability cannot be changed in any other form. So, so this is an example of overriding um, a function. So we have a base contract which defines the foo function, okay, and the derived contract which will override the foo function. So please note that here the base function is defined as virtual. The derived contract defines the foo function as override. So when we call the foo function in the derived contract, we should not see this string, but this one. Okay, so we deploy the derived contract. And we call foo. Perfect. So we read this is the derived contract function. Okay, this is the overriding. We are namely overriding the function of the base contract in our derived contract. Okay. Then we have also the possibility to override the modifier. So this works very similar as in the function overriding, but there is no overloading for modifiers. And of course, we have to define the virtual keyword in the modifier to be overridden and override in the modifier that it is overriding. Okay, this is an example of a modifier. We have the foo modifier. Here we are overriding the foo modifier in the inherited contract, which is the derived contract and inherits from the base contract. Then we talk about construct. Okay, this part is essentially repeating some stuff that we have said earlier. So the constructor, which is an optional function that is marked with the constructor keyword, and it is executed when the contract is created. So it is used to initialize some variables in or to perform some initial operations when you deploy the contract. So before the execution of the constructor code, the state variables are set to their specified values if they are initialized in line, otherwise they are set to their default values. Once the constructor has finished executing, the final code of the contract is deployed to the blockchain. The deployment of code incurs additional gas costs proportional to the length of the code. This code encompasses all functions that form part of the public interface and all functions that can be accessed from there via function calls. So it basically means public functions and external function, and does not include the constructor and the internal function that are all invoked from the constructor. If we do not define a constructor, a standard constructor equivalent to empty curly braces, empty block will be created. So this is an example of a constructor, very simple, that we have seen, of course, in other examples. Here we can also check this out. So here we, in the A contract, we set an initial value for this A variable, this constructor. Here in the derived contract, which is B, that is extending A, we are calling the constructor A with 1 as parameter. So we expect that if we deploy B, the value of A should be equal to 1. So we deploy this contract, the B contract. Okay. Okay, the value of A is equal to 1. Then we have the possibility to define also abstract contract, much like abstract classes in Java. So a contract must be marked as abstract when at least one of their function is not implemented. So you have not a total abstraction like with interfaces, but a partial abstraction, or when they do not provide arguments for all their base contract constructor. So even if this is not the case, a contract may still be marked as abstract, such as when you do not intend for the contract to be created directly. So abstract contracts are similar to interfaces, but an interface is more limited in what it can declare. An abstract contract is declared using the abstract keyword, as in this case. So, of course, abstract contract cannot be instantiated directly. This is like in Java, you cannot create an object from an abstract contract because it is partially implemented. You cannot deploy a contract that is partially implemented. It must implement all of its members, all of its functions. Um, so this is also true if an abstract contract itself does implement all the defined function. This is an example of usage of an abstract contract here, where we are overriding the function foo defined only not implemented in the abstract contract. So if we also test this contract, we should see um, the foo function should return my string. Okay, here it returns my string, so the overrides of the base function, it is working. So if a contract inherits from an abstract contract and does not implement all non-implemented function by overriding, it needs to be marked as abstract as well. For example, here, if we do not override, do not implement this function, we should mark this contract as abstract. Here it talks about how the abstract contracts decouple the definition of contract from its implementation, and this is useful to implement the template method pattern, which is a design pattern, and that use and also can be used to, for example, removing code duplication, because we can put, for example, the code common to more contracts in an abstract contract, and avoid to write the code, the same code more than one time. So we just write it once. And so abstract contracts are useful in the same way that defining methods in an interface is useful. It is a way for the designer of the abstract contract to say any child of mine must implement this method. Okay, interfaces are similar to abstract contract, but they cannot have any function implemented. It's like in Java where you say interface is like contract that you make who is implementing with the contract that are implementing the interface, because you make sure that the contract that will implement this interface will have all the methods that are listed in the interface. So each is just we are uh, we are enforcing what are the mm, let's say the rules that the derived contract must have. By rules, I mean the methods that the that the contract that implement this interface must have. So there are some restrictions, like interface cannot inherit from other contracts, but they can inherit from other interface. All declared functions must be external in the interface, even if they are public in the contract. They cannot declare a constructor, they cannot declare state variables,
they cannot declare modifiers. To create an interface, we make use of the interface keyword. So you see here the interface. So contracts can inherit interfaces they would inherit other contracts. All functions declared in interface are simply implicitly virtual, and any function that overrides them do not need the override function. This is not how This does not automatically mean that an overriding function can be overridden again. This is only possible if the overriding function is marked as virtual. Interface can inherit from other interfaces. This is has the same rule of the normal inheritance, as you can see here. You have a parent A interface, a parent B interface, and a sub interface that inherits from parent A and parent B. For example, we can take the same example that we have seen before, and we can transform it, transform the abstract contract in an interface. So here we put interface. Okay, this is automatically virtual. This must be declared as external. Okay, now that should this compiles, so we can deploy the second contract here. The contract B. Okay, now if we call foo, like before, it should return my string. Perfect. So now we can discuss a little bit the libraries. Libraries are used to allow for code reusability. For example, if we need to implement a custom authentication logic that multiple contracts needs to use, we can put this logic in one library and then import the library in all the smart contracts that need this authentication logic. So any updates or improvements to the authentication mechanism can be made in the library, and all the smart contracts using the library will automatically benefit from these changes. Libraries are similar to smart contracts, but they are restricted in the following ways. They cannot have state variables, they cannot inherit nor be inherited, they cannot receive either, they cannot be destroyed. If library functions are called, their code is executed in the context of the calling contract. As a library is an isolated piece of source code, it can only access state variables. Library functions can be called directly if they do not modify the state, so if they are marked as a view or pure, because libraries are assumed to be stateless. In the following example, we illustrate how to use libraries. We first create a file called matlib.sol, which contains our library. This library is declared using the library keyword, as you can see in here. So it is similar to our contract. Instead, here we have the library keyword. We have defined some function, for example, sum, subtract, multiply, divide. So this for function, and we put this in Remix in a file called matlib.sol here. Okay, this is our file with our library. Then we can import the library in our contract with the import statement. So here, let's say that we want to create a new a contract that makes use of the matlib library. We just use here import matlib.sol, and for example here I have created some tests with some assertion. For example, here we call the matlib sum function. We sum 10 to 5. We expect that the sum is 15. We subtract 5 from 10. And we expect the subtraction is 5. Multiply 2 times 5 and the result should be 10. We divide 10 by 2 and the result should be 5. So we just need to deploy this contract here. In fact, no, I don't. It is calling to confirm another time the transaction. Okay. So now that we have deployed our contract, we can call the test function here. Okay, the test function went fine. So we can create our library in a file here with the same name, for example, import this file in another contract and use it however we like. So in this allow us to avoid to duplicate the code. And this is what it is used for some math libraries, for example, by OpenZeppelin. Then there is another directive which is the using for. So we can write using A for B, and is used to attach the library function from the library A to a type B in the context of a contract. This function will receive the object they are called on as their first parameter, and this is similar to how the self variable works in Python. For example, we can rewrite the previous contract, this one, using the directive using for. So we import the matlib.sol. Here we are extending the doing type by adding to this type the methods of the function of this library here. So this allow us to call, for example, we define a uint a equals 10, we call a.sum. So it is like that the sum function of this library can be used in this in this variable uint with the dot operator, since we have stated here using matlib for uint. Okay, then I have performed so it is like that we can replace matlib.sum as we have seen earlier with a dot sum b. Okay, also this contract can be tested. Then I made some assertion for the sum, for the subtraction, for the multiplication and division. Okay, the same as before. So we can deploy this contract. We confirm. Okay, the contract has been deployed. Now we call the test function. Okay, perfect. It is working. So here we are demonstrating also how to use this other type of expression.
So guys, we have reached the end of the video. I hope that it has been useful to you and that you have learned a lot. I encourage you to comment below what are your opinions about this video, what have you liked and what not, and what in your opinion would be improved in the next video. So thank you for watching and see you in the next video.